My name is Rushabh and I'm gonna talk about the topic order of homogeneous equation from subject ordinary differential equation and vector calculus. I am from CSE AML branch second semester. In this slide we are gonna discuss about what is a differential equation. Before we even get to a homogeneous equation, we need to establish what a differential equation is because everything builds from this foundation. A differential equation is an equation that contains an unknown function and one or more of its derivatives. Instead of solving for a number like in algebra, you are solving for an entire function. For example, if you know that the rate of change of population is proportional to the population itself, you write that has dp by dt is equal to kp, and solving that gives you pt is equal to p naught k power e power kt, where p naught is the initial population and pt is the population after t time. The derivative in the equation is what makes it differential equation. They appear everywhere in engineering, physics, biology, and economics. Anywhere a quantity changes continuously over a time or space, understanding them is a fundamental to understanding how the physical world actually behaves mathematically. On this slide, we are going to discuss about what does order mean in differential equation. The order of a differential equation is defined as the order of the highest derivative present in the equation. This is one of the first thing you identify when looking at any differential equation. If the highest derivative in the equation is dy by dx, a first derivative, it's a first order equation. If the highest derivative is double differentiation of y, it is a second derivative. It's a second order equation and so on. For example, dy by dx plus 3y is equal to 0 is first order. Double differentiation of y plus dy by dx plus 6y is equal to 0 is second order differential equation. The order is critically important because it determines how many initial or boundary conditions you need to find for a unique solution, and it directly determines the number of arbitrary constants in a general solution. A second order equation will always have two arbitrary constants in its general solution. In this slide, we are going to discuss what is a homogeneous equation, the core definition in a mathematical terminology. The word homogeneous in differential equation has a very specific and precise meaning, and confusingly it means slightly different things in a different context. So let's be exact. For a first order ODE of the form dy by dx is equal to fxy, the equation is called homogeneous. If the function fxy can be expressed purely as a function of the ratio of y by x, that is fxy is equal to g y by x function for some function g. Equivalently, f of xy function is a homogeneous function if f tx comma ty function is equal to tn fxy function for some power n called the degree. For a linear ODE, the equation is homogeneous if the right hand side is 0, meaning there is no forcing function or source term. Both definitions come up in coursework and they are different. Always check which type of homogeneous equation is being discussed based on the context. On this slide, I'm going to discuss about the homogeneous function, the mathematical foundation. To fully understand the homogeneous differential equation, you must understand homogeneous functions. A function f x comma y is said to be a homogeneous of degree n if replacing x with tx and y with ty scales the function by t power n of a function f tx comma ty is equal to t power n into a function f x comma y. For example, if we take a function in terms of x and y is equal to x square plus xy plus y square and replace x with tx and y with ty, t square x plus t square xy plus t square y square will be the equation after substituting x and y in terms of tx and ty. We have to take t square common. From that we'll get t square bracket open x square plus xy plus y square bracket close. So this is a homogeneous of degree 2. If the function x comma y is equal to x cube plus y cube is a homogeneous of degree 3. If a function x comma y is equal to x square plus y plus 1 is not a homogeneous because a constant term 1 doesn't scale with t. The key insight is that if both mx comma y and nx comma y in the equation m dx plus n dy is equal to 0 are homogeneous function of a same degree, then the whole equation is a homogeneous differential equation. The degree of the function does not have to be any particular number. What matters is that both m and n have the same degrees. In this slide, we are gonna see how to recognize a homogeneous ODE visual test. There are a practical visual method to check if a first order ODE is a homogeneous. Write the equation as dy by dx is equal to a function f x comma y. Now try to express f x comma y entirely in terms of v is equal to y by x, or equivalently substitute y is equal to vx and see if x cancels completely. If after the substitution every x disappears and you are left with a function of v only, the equation is homogeneous. For example, if we take a dy by dx is equal to x square plus y square by xy. Divide the numerator and denominator by x square, so it becomes 1 plus y by x whole square by y by x, and we know that y by x is equal to v square, so we have to substitute v here. We will get 1 plus v square by v. Every x has disappeared and this conforms, it's homogeneous. If any x remains that cannot be observed into y by x ratio, the equation is non-homogeneous. This test is fast and reliable and is the standard approach used in solving exam problems. In this slide, we are gonna see about the standard method, substitution. Y is equal to Vx. Once you have conformed a first order ODE, a homogeneous, the solution method is always the same. Substitute y is equal to Vx where v is the function of x. This is a fundamental substitution that transforms homogeneous ODE into a separable ODE, which is much easier to solve when y is equal to Vx. Differentiating with respect to x using the product rule gives dy by dx is equal to v plus x dv by dx. You substitute both y is equal to vx and dy by dx is equal to v plus x dv by dx into our original equation. Because the equation is homogeneous, all x terms cancel after the substitution, leaving an equation in v and x form. This resulting equation is separable. You can pull all the v terms on the one side and all the x terms on the other side, then integrate both the sides. After integrating, you back substitute v is equal to y by x to express the solution in the terms of original variable x and y. In this slide, we are seeing a worked example 1, solving a first order homogeneous ODE. Let's solve dy by dx is equal to y square minus x square by 2xy. Step by step. First, verify it's a homogeneous. Divide the top and bottom by x square to get dy by dx. After substituting the y by x, we get y by x whole square minus 1 by 2 by y by x. So after that we get v square minus 1 by 2v. Yes, it's a homogeneous. Now substitute y is equal to vx so that dy by dx is equal to v plus x dy by dx. The equation becomes v plus x dv by dx is equal to v square minus 1 by 2v. Rearrange x dv by dx is equal to v square minus 1 by 2v minus v. V square minus 1 minus 2v square by 2v is equal to minus v square minus 1 by 2v. Separate variables 2v by v square plus 1 dv is equal to minus 1 by x dx. Integrate both sides, so we will get ln v square plus 1 is equal to minus ln x plus c. This simplifies to ln v square plus 1 plus ln x is equal to c, or x open bracket v square plus 1 is equal to a, where a is a constant. Back substitute v is equal to y by x. We get x bracket open y by x whole square plus 1 bracket close is equal to a, which simplifies y square by x plus x is equal to a, or y square plus x square is equal to ax. That's a general solution. In this slide, we are going to see the difference between order and degree and understand the difference. Students often confuse order and degree. These are the two completely different classification of differential equation. Order, as we have established, is the order of the highest derivative. Degree is the power of which highest order derivative is raised. After the equation has been cleared of the fractions and radicals involving the derivatives, for example, double derivative cube plus dy by dx is equal to x has order 2. Highest derivative is second order and the degree is 3. The second derivative is cubed. Dy by dx plus y is equal to x has order 1 and degree 1. Under root dy by dx is equal to x plus y. To find the degree, square both sides, you will get dy by dx is equal to x plus y whole square. Now degree is 1. Important degrees is only defined when the equation is a polynomial in its derivatives. If the equation had terms like sine dy by dx or e power double derivative of y, the degree is undefined. Order is always defined. For homogeneous equation, both the order and the structures, the equation together determine which solution method applies. On this slide, we'll get a full picture of what is first order homogeneous equation. Let us consolidate the complete theory of the first order homogeneous ODS. The equation m x comma y dx plus n x comma y dy and is equal to 0 is a homogeneous when m and n are both homogeneous of the same degree n. The substitution y is equal to vx or equivalently x is equal to vy for cases where dividing by x causes issue. Always reduce it to a separate equation. The general solution will always contain one arbitrary constant. Consistent with first order. Geometrically, the solution curves of a homogeneous first order ODE have a special property. If you scale x and y by the same factor, that is, move along any ray from the origin, the slope of the solution curve is same everywhere along that ray. This means the isoclines curve or the constant slope of a homogeneous ODE are always straight lines to the origin. This geometrical insight helps you to sketch solution curves and build intuition of the behavior without even solving the equation. Second order homogeneous linear ODE. This is where the topic expands significantly and connects to a wide range of real application. A second order linear homogeneous ODE has a standard form: ax double derivative of y plus bx single derivative of y plus cx into y where is equal to 0, where a, b, c are the functions of x or constant, and the right hand side is 0. That 0 is what makes it a homogeneous in a linear sense. The general solution of any second order linear homogeneous ODE is linear combination of two linearly independent solutions. Y is equal to c1 y1x plus c2 y2x. This results come from the superposition principle, which holds because the equation is linear. The two constants c1 and c2 are determined by initial condition for an IVP or a boundary condition for BVP. Finding those two independent solutions y1 and y2 is a central challenge, and the method depends on whether the coefficient are constant or a variable. In this slide, we are going to discuss about the application, why homogeneous ODEs matters. The reason we spend so much time on homogeneous equation is that they model the natural, unforced behavior of physical system, what a system does on its own without external input. Spring mass system, m double differentiation of x plus x single differentiation x plus kx is equal to 0, describes a mass on a spring with a damping C. The three cases, overdamped, critical damped, and underdamped, correspond directly to the three characteristics root cases. RLC circuits. The charge in the series RLC circuit with no voltage source satisfies L double derivative Q plus R single derivative Q plus 1 by C into Q is equal to 0. Mathematically identical to a spring mass system. Heat conduction. The special part of the heat equation leads to homogeneous ODEs with a boundary condition. Population dynamics, single derivative is equal to ky is the simplest homogeneous first order ODE, describing unconstrained exponential growth or decay. Quantum mechanics, Schrödinger equation in a certain geometrics reduced to homogeneous ODEs like Bessel's equation or a legendary equation whose solution are famous special function of mathematical physics.